Everyone, my next series of lecture is going to be on application of thermodynamics, and today's subtopic is partial molar properties and chemical potential. Now let's start with partial molar properties. It is also known as the partial Molal quantities. Now let's take any extensive thermodynamic property X. That means this is some property X which is definitely dependent upon the amount of the substance. If it would have been some intensive property, then it would only depend upon pressure and temperature and not on the amount of the substance. But since it is an extensive property, then along with its dependence with pressure and temperature, it will also depend upon the number of moles of the different components, and hence mathematically it can be expressed as it is a function of temperature, pressure, and number of component of the first component, number of moles of the second components, number of moles of the third components, and so on. So if dx is a perfect differential, then dx can be expressed this way, del x by del t at constant pressure n1 n2 dot 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 dt. That means the rate of change in that property with respect to temperature at constant pressure and keeping the other components constant, multiplied by the overall change in temperature, this way. So all these functions, any one will vary and others will remain constant. This way the overall change, when summed up, then the value of dx can be obtained. So here this del x by del ni into dni at constant temperature, pressure, and Nj. This property is known as the partial molar property or the partial Molal quantity. Now what about I and J? First of all, I is not equal to J. That means when I is the first component, then J are second, third, fourth, etc. these components. If I is the second component, then J is first component, third component, and other components. If I is the third component, then J are first, second, fourth, and so on, these components. So this way, this property or the next any one of them are the partial molar property. That means the rate of change in that thermodynamic property, it may be Gibbs free energy, it may be enthalpy, it may be entropy, whatever it is. So according to that, its name will also change. Suppose if it is Gibbs free energy, then it is partial molar free energy, okay, or partial Molal free energy. Both the molar and molal term you can use here. But the fact is that if it is the system is consisting of more than one component, then the rate of change in that particular thermodynamic function with respect to change in any one component by keeping the other components constant. Okay, so this is the partial molar free energy with respect to that particular component. So it can be defined as the increase in x. Increase means the rate of change with the positive change, so it is called increase in change. So the increase in x per mole due to an infinitesimal addition of ith component to the system, keeping temperature, pressure, and all other components constant. So this is known as the partial molar property or partial Molal quantity. Now we have already the equation of dx, the mathematical expression of dx, and from that expression, if temperature and pressure parts are kept constant, then the first term and the second term of the right hand side of that equation particularly becomes 0, and from the third term we can continue that equation. That means if temperature and pressure remains constant, that means dx suffix t comma p. Okay, and look at the right hand side, the first term and the second term have vanished, whereas this third, it has started from the third term. Okay, so we can express that equation in the new form like this. And here this part is written as x1 bar. Okay, this part within the parenthesis is written as x2 bar, and this way so on according to the third component, the fourth component, and so on. Now this xi bar, what does it refer to? Okay, so it refers to as the partial molar Gibbs free energy. You can also say partial molal Gibbs free energy. Both are same, both the terminologies have the same meaning. Okay, so if it represents G, that means Gibbs free energy, then it is partial molar Gibbs free energy or partial molal Gibbs free energy. It is denoted as Gi bar. Similarly, partial molar Helmholtz free energy, okay, it is Ai bar. Partial molar enthalpy, Hi bar. Partial molar internal energy, Ui bar. Partial molar entropy, Si bar, and partial molar volume, Vi bar. Okay, so we have 6 partial molar properties or partial Molal quantities, and their respective expressions are, just in the place of x you insert the corresponding thermodynamic function. Now if it is G, then it becomes Gi bar. If it is A, it becomes Ai bar, and so on. So we have overall 6 partial molar properties. Now out of these 6 partial molar properties, this part, only this part, okay, only this part is also known as the chemical potential, okay, and the other 5 are not chemical potentials. They are only the partial molar properties. Only this partial molar property is similar to the chemical potential of the system. You have to keep in mind that the constant terms are, along with Nj, are particularly temperature and pressure, okay, and if temperature and pressure only are kept constant, then all the other properties except G remain as the partial molar property, but in case of G only it becomes the chemical potential. Okay, so we have 6 partial molar properties, out of which one is common with the chemical potential expression. So there should be a question whether the expression of chemical potential is possible with respect to the other energy terms such as Helmholtz free energy, enthalpy, or internal energy. These two are not the energy terms, so actually chemical potential expression is not possible with respect to S and Vi. But is there any possibility to express chemical potential in terms of A, H, or Ui? Okay, let's see. Now, as I've said, our next topic of discussion is chemical potential, and the term partial molar free energy is known as the chemical potential, as I have said, and the corresponding expression of Gi bar is this. Now, since it is also known as the chemical potential, so this can also be symbolized as mu I. So Gi bar and mu I are the same. If you write Gi bar, you are meaning the partial molar free energy, and if you are writing or symbolizing as mu I, then you are meaning the chemical potential, but the expression or the physical significance of both are same. So it may be, what should be the definition of this term mu I? So it may be defined as the increase in free energy of a system due to infinitesimal addition of one component of the system, keeping temperature, pressure, and other components constant. Isn't it? That means it is actually the rate of change in G with respect to Ni, keeping P, T, and Nj constant, I not equal to J. So this is actually the definition of chemical potential with respect to Gibbs free energy. Okay, but the terms Ai, Hi, Ui, Si, Vi with bar are not chemical potential, as I have said. They are not chemical potentials. They are only the partial molar properties. However, the expression of chemical potential in terms of Helmholtz free energy, enthalpy and internal energy is possible. So we have actually the expression of dx. Instead of x we have written here g. So del g by del t is actually minus s. So here minus s is written and it is multiplied with dt. Similarly, del g by del p is actually plus v. So this first and second terms of that equation becomes minus st s dt plus v dp in case of g, and in case of g, the from the third term it becomes g1 bar dn1, g2 bar dn2 and so on, and thus we get equation 1. Now we know that the expression of Helmholtz free energy or work function is A equals to U minus Ts. Now U has also the expression H minus PV. So this H minus PV is inserted instead of U, and in place of H here we have written G plus Ts, because actually G has the expression H minus Ts. So H should have the expression G plus Ts. So instead of H we have written here G plus Ts, and here minus PV and minus Ts remaining the same, and this plus Ts and minus Ts would cancel each other, then only minus PV term remains here in this equation along with G. So finally we have got the expression of A as G minus PV. Okay. Now if the derivative of A is taken in the left hand side, then the derivative of the right hand side should be dg minus pdv minus pdv. Now dg has this expression, this right hand side expression in equation 1. This value must be put here. So we have put the value of dg from equation 1, and here I must say that this vdp minus vdp cancels this plus vdp here. Okay, and minus sdt and minus pdv terms remains the same here. That means uncancelled. So the uncancelled terms are minus sdt and minus pdv, whereas pdv has been cancelled. And the third term, this is the third term, this is the second term, and so on. Now if you find here temperature and volume is kept constant, then this part becomes dA at constant temperature and volume, and these two parts would vanish, because at constant temperature dt is 0, at constant volume dV is 0. So if both temperature and volume are kept constant, then the first term and the second term would vanish, and this way you will get this expression. And if both sides are divided by d and I, then it has the expression like this: partial differentiation of A with respect to Ni at constant volume, temperature and Nj, where I is not equal to J. Then this is another expression of chemical potential, mu I. This is actually same to del G by del Ni P T Nj. So in the expression of chemical potential, if you express it in terms of G, then the constant terms are P and T along with Nj. But if you express this in terms of A, then the constant terms are V, T along with Nj. Now both have the similar magnitude. Expressions are different, but the magnitude is same. Both are mu I. Okay. So similarly you can find out the expressions of mu I in terms of H and U. Let's see how we can do this. Before that, the definition, the second definition of chemical potential, let us extract the definition from this mathematical expression. So what should the definition be in terms of A? That means it is the increase in the value of A with respect to infinitesimal addition of any one of the components, keeping volume, temperature and other components constant, isn't it? So let's write this. So this is the definition, the increase in work function or Helmholtz free energy of a system due to infinitesimal addition of one component of the system, keeping temperature, volume and other components constant. So let us differentiate this expression with partial molar Helmholtz free energy. In partial molar Helmholtz free energy, that means AI bar, you will find that the pressure temperature parts were constant, but here in the chemical potential part, the volume temperature remaining the constant. So that is the difference between partial molar Helmholtz free energy and chemical potential in terms of Helmholtz free energy. Okay, I repeat here, in the expression of partial molar free energy, Helmholtz free energy, AI bar, there the along with temperature, the pressure term is constant along with Nj. But in the expression of chemical potential, along with Nj and temperature, the volume part is constant. That's the difference. Now let's proceed for enthalpy. So enthalpy has the expression G plus Ts, because G is H minus Ts, so H must be equal to G plus Ts. Taking derivatives for both sides, we get in the right hand side dg plus tds plus sdt. Now putting the value of dg from equation 1. This is the value of dg from equation 1. Okay. Now this sdt terms have been cancelled by this plus sdt term, and the uncancelled terms remaining vdp and tds. So from this, if you keep this entropy term and pressure term constant, then the first and the second terms become 0. That means these two terms would vanish. Okay, and from the third term you would get the penultimate step of getting the expression of chemical potential. Penultimate, the word penultimate is used the last before. Okay, that means the final expression, there is some step that just the earlier step of that final step is the penultimate step. Okay, that's why I've used the term penultimate here. Anyway, so this is the penultimate step. Okay, so dH at constant entropy and pressure. Look, in the HI bar expression you had temperature and pressure, but here entropy and pressure, not temperature and pressure. And here is the final expression, which is known as the chemical potential. The magnitude is same, but the expression is different. This is the third definition, third mathematical expression of chemical potential, which is actually in terms of enthalpy. So let's define it. And the definition is the increase in enthalpy of a system due to infinitesimal addition of one component of the system, keeping pressure, entropy and other components constant. Okay. Similarly, the same thing in case of U. U equal to H minus PV equal to G plus Ts minus PV, putting the value of G, dG plus TDS plus SDT minus VdP minus VdP. Okay. No, this is not putting the value, just this is taking the derivative of both sides. Okay. So taking the derivative of both sides, here in the left hand side du, and in the right hand side you have 5 terms, so 5 expressions, dg plus tds plus sdt minus vdp minus vtp. Now putting the value of dg from equation 1. So putting the value of dg within the parenthesis, and now cancelling terms are sdt and vdp, both would be cancelled, and the uncancelled terms would be tds plus sdt. Okay, and this way tds minus pdp, oh sorry pdp would be the uncancelled term. Okay, here sdt also got cancelled, and here you find, so what terms are you going to keep constant? The terms you are going to keep constant are entropy and volume. In the UI bar expression you kept constant pressure and temperature. Here neither pressure nor temperature, you are keeping entropy and volume constant. Okay, so this way you are getting the final expression of chemical potential. This is the fourth expression of chemical potential, and it has the definition: the increase in internal energy of a system due to infinitesimal addition of one component of the system, keeping entropy, volume and other components constant. So the mathematical expression of mu I together, we have 4 expressions. These are the 4 expressions. First in terms of G, second in terms of A, third in terms of H, and fourth in terms of U. So these are the same things. Okay, these have the same magnitude, but the expressions are different. So that's all for today. We have discussed what is partial molar quantity, partial molal quantity or partial molal quantity, and what about chemical potential. So chemical potential has 4 expressions, out of which this part, the expression in terms of G, is also known as the partial molal free energy or partial molar free energy. And also we have got other 5 expression of partial molar properties. Okay, so that's all for today. Thank you.